Good morning, everybody. My name is Testani, and I'm going to present a thermal protection system for re-entry CubeSat. The re-entry CubeSat in subject is Karman, about which I just listened to the presentation from my colleague and Umit. So maybe I can go quickly through the first slide describing the mission. Just a couple of remarks to better understand my presentation. The mission is going to have basically two relevant phases from the thermal point of view, which are the orbital part, especially for the differential drag maneuver part, so this part more or less, and also the re-entry part, which is the most interesting and challenging from the thermal point of view, because the satellite is going to experience an extremely harsh environment from a thermal point of view, with very high temperatures, which can go above 2000 kelvins on the front part, on the front core part of the satellite. So for to achieve the mission objectives is fundamental to adequately insulate all the parts necessary to survive up to the end of the mission. And this is achieved through different ways or techniques, if you prefer, to thermal insulate the satellite. The first one will be the presence of cork nose of the satellite, which you see here, which is approximately of the size of 1U of CubeSat, even if it's not completely full, because inside will be hosted a spectrometer for measurements during re-entry. And currently, we just finished a test campaign at the Von Karman Institute with plasmatron facilities we have, and also many simulations in order to define the shape and the material. And this analysis led us to choose the P50 core, which is, as I said, an ablative material capable to shield the satellite from the high temperature you will experience. A second stage of protection is provided by the ceramic walls, which are basically surrounding the entire internal parts of the satellites. We will have basically three different ways we are using the ceramic plates. A lateral protection, the yellow one, which is it could be in silicon carbide or OXCMC. The trade-off is still in progress, but we do not expect big differences in thermal performances. And also two plates will be placed on the front. Sorry, wrong button. On the front part and back part, in order to still insulate the satellite. The front one is necessary to thermally decouple the internal environment of the satellite from the ablative shield, while the back part is here to again insulate the internal part, because here we replaced the hinges for the deployable panels, through which some hot flows can come in. So it's absolutely necessary to lock this part. And the last stage of protection is provided by these boxes we call the survival unit, in which we are going to place all the electronic components necessary to survive to the re-entry phase. Those components will be the OBC, the batteries, the iridium comm system, including the antenna, and the data acquisition board also, which are placed in this front survival unit, and this is the main one. The insulation is achieved with aerogel, which is an extremely lightweight and insulating material, which is already space qualified. And that insulation layer will be enclosed in a titanium box, which has the dark blue line you may see there. Why titanium? Well, for the optimal thermal performances, and also because it's a 3D printable material somehow. There are techniques to do that, which gives more freedom to optimize the shape of this box in order to house it inside the satellite, because as you can see, it's quite packed configuration. Then we don't use titanium to surround the iridium antenna in order to avoid RF interferences, but we go for ceramic material also there. This part is actually still under evaluation, so we might change slightly in order again to optimize the EMC, and some tests will be performed at the Delft University facilities in the coming months. But let's have a closer look to the survival unit concept. So as you see, the PCB inside, the dark blue one, will host all the electronic components, and the iridium antenna, black cylinder here, will be directly connected to it. This PCB will be sticked directly to a thick aluminum plate with purpose of heat sink. So capable to store some thermal energy and also to distribute uniformly the temperatures during re-entry. You see the transparent layer, which is the aerogel insulation with a minimum thickness of 7.5 millimeters, which has been identified the minimum one to provide sufficient protection during re-entry. And everything is enclosed in this titanium box. The titanium box is the purpose also to be the mechanical interface to the rest of the satellite, because the aerogel is actually a quite brittle and soft material, so it's basically impossible to mechanically connect it with screws or spacers or any other way. So we basically need a mechanical interface, and we decided to go with that solution. The old box is then thermally insulated thoroughly from radiation and conduction point of view, using some low emissivity coatings, and also the spacers will be made in Teflon. That with all the purpose of this is to heavily insulate and completely thermally decouple this unit from the rest of the satellite, which is of great importance during re-entry. To validate the design, some thermal analysis has been performed. So here you can see just a few pictures of the thermal model and the way we model the survival unit inside and the thermal collections. I could speak for, I don't know, a couple of months about all the details implemented in the thermal model, because it's very important to have a highly refined thermal model, since the environment is extremely demanding from this point of view. The boundary conditions applied are instead derived from CFD analysis, from which we see that the highest temperature will be experienced on the front cork, and they could go above to 2000 Kelvin. As you see, luckily the side walls of the panels are a little bit lower, and anyway, this is a worst case scenario, so the actual temperatures might be actually a bit lower. That's from the boundary conditions. From our point of view, we need, for some reasons, to keep on the iridium transmission always on during re-entry. The reason is why the plasma sheet surrounding the satellites during the space is basically preventing the comm system to communicate. So we don't actually know exactly when we will be able to transmit. So we just need to keep on trying when we succeed. So there's another way that trying to transmit every time, and that will mean that we will have a continuously 3.5 watts of heat dissipation inside, which is not for sure not helping in sizing the TPS system. The simulations done shows those results. So up to the land crash, we're basically able to keep all the electronic components below the temperature limits. The initial conditions here are derived from a steady state analysis of the orbital case in low power mode, which is actually the mode in which the satellite will be just before the re-entry phase for a while. Of course, the iridium component is higher temperature with respect to all the rest of the electronics, but still at the end of the re-entry phase it will be below the temperature, the operative temperature limit. What will be out slightly of the temperature limit are the batteries, but only because the temperature is around 50 degrees at most. Luckily, it means only that the temperature performance will be degraded and probably the recharge is a bit compromised. But I mean, it's the last use of batteries we will have, so this is not going to be a problem. ESA during the PDR review asked to perform some breadboard testing to see the heat stress on the batteries during re-entry to actually assess that this going out of batteries is not a problem. Those tests are currently scheduled for the coming months, so I cannot show results about, but I hope I will in some next occasions. In conclusion, I show you that there is also a front survival unit, which is a small one on the top of the satellite, which is placed the data acquisition board. This box here is less insulated than the main one, let's say. In fact, the temperatures will pass the maximum operative limit at around 11 minutes, so they will not survive up to the end of re-entry. This is actually within the boundaries, within the requirements for the science mission, because up to that time we will reach an altitude and we are measuring for enough time to get good science data, and we already transmitted those data to the main PCB and stored them, ready to be transmitted through Iridium. So this is actually not an issue because we are already finished at our data acquisition at that point, so it's basically free to burn. Then, of course, this design must be consistent with the orbital part. So for that purpose, some hot case and often called worst cases analysis has been done. I mean, nothing different than the usual analysis done for CubeSat. So definition of worst case attitudes and worst case orbits. That must be anyway within the QB50 boundaries. And that led us to those results where basically all the components outside the survival unit are well below the temperature limits. Only the GPS unit is slightly close, but not above the temperature limit. Anyway, the GPS can be somehow duty cycled to lower this a little bit. And what's interesting is also that the survival unit is actually thermally decoupled from the rest of the satellite because it's not feeding at all the temperature cycling. This case presented here is from the folded configurations, but we have also deployed configurations. But we have also part of the mission in folded configurations for the differential drag analysis. If you remind the presentation of Earth and Newman 3 minutes ago. And also here, basically, we see the same things. This peak here may look weird, but it's actually just switching on a full powered communication system to see the effect, like a very worst case scenario. But as you see, it increases of around 10 degrees, is compromising the thermal design of the satellite. Again, the survival unit components are basically thermally decoupled from all the rest of the satellite. Cold case is also leads to the same conclusions, so the minimum temperatures also are above the temperature boundaries, both in deployed and folded configurations. So let's go quickly through the conclusion. What I wish to have communicate to you is that it's actually feasible to design thermal protection system for re-entry, even for a CubeSat size satellite. We choose this solution, so the survival unit, providing high insulation, the presence of an heat sink, which is necessary, we realized, and with the purpose to save only the necessary components to achieve the mission. So, for example, the DCS is not going to be used, so we can afford to lose it at the end. This for the survival unit. Nevertheless, is not enough, but also the rest of the satellites may be externally insulated. So the presence of an ablative material is absolutely necessary, and also the walls insulation is necessary as well. What is also important to remark is that there are actually concurrent requirements, because if from a certain point of view we want to insulate completely the satellite from the environment for the re-entry part, for the orbital part we actually need to dissipate some extra heating coming from electronic components, for example the DCS units or the GPS. So we need to find a way to achieve both those tasks, which is actually literally on opposite point of view from a project point of view. Then we are currently just over the PDR. We passed the PDR at ESA a few weeks ago, and we are now preparing the assembly phase of the engineering model. So we will go with a model to the CDR, and for the CDR, well, we want to finally consolidate the design, because there are still some things that might be improved, we believe. So we are keep on working on this. Thank you for your attention, and thank you also for the entire Carmen team, which is giving me the chance to experience this new task of the thermal design, which is quite new for me. To ULG, which is supporting me a lot for the thermal design, and also to ESA for funding the project and giving us this chance. Thank you very much.
Swiss Space Center, UFL. I have a question or like a comment. I think you have taken account that it will be high temperature not only on the top of your satellite but on a dome on the backside. So in your tests it is impossible to simulate this situation, and so I think we have made some additional tests, because you will have a high temperature inside because of the heating from the dome.
That is correct. What I show here in this picture, I go quickly back. The test inside the plasma drum facilities for the core was actually to qualify the material. So it was a part of the trade-off breadboard testings for choosing the best solution of the core material. Of course, it's not a test to certify the thermal environment behind the cork insulation, but the purpose was just the material selection. So we tested different materials, our colleague Ligil Sakakera did, and we came up with the choice of the P50 for many reasons, because we believe it's better. But yeah, we are perfectly aware that it's not actually at the back we are not having the temperature profile we will normally with that during the end. But thank you for your comment.
Yeah, and just the second question: did you calculate the point of landing, or what's your plan about how to catch this re-entry part?
Well, actually we are not planning to retrieve satellite after landing, but we, below 44 kilometers, according to our simulations, the plasma sheet should not be there anymore, or rather should be weak enough to allow us to communicate with iridium constellations. So below this altitude we are going to transmit all the data with some techniques that my colleague at UMIT is refining, in order to send all the data collected in the previous phases, but after the landing crash mission is over, so we're not going to be looking for the satellite, or not even transmitting actually after landing.
I just want to ask, first thing, thank you for a very interesting presentation. Two questions. Since the re-entry issue is quite new, I mean, you want to make sure that you will work during and after the re-entry. I believe that you would have to create a certain model that you would test a fully functional satellite, but not probably the PFM model, or think about PFM model tested inside the chamber. That should be very interesting to see.
Yes, I agree. That's for sure very interesting. The VTI facilities probably are not, let's say, optimized for a full CubeSat size test, but it's something we are thinking about. Nevertheless, we wish to test at least the entire survival unit for the day flows. So there is a test plan. I didn't present it, but it's there. In which we want to see, first of all, the actual insulation we can achieve with this titanium plus aerogel plus vacuum plus heatsink, so which is actually the thermal profile we expect through a certain wall like this, and then to assemble an engineering model of the survival unit and fully tested it to the expected day flows. That will be for sure in our plans.
Yeah, that'll be very interesting. Thank you. And the other thing was, since you insulate heavily the sunlight, you showed that you have some thermal issues during the operation. You have a problem with getting the heat out of the spacecraft because it's actually very insulated. Do you have any ideas on how solving it? Do you have any leads in the way you want to look at? Or,
Well, currently the simulation shows that with the duty cycle we choose and the orbital condition we should experience, even in the worst cases, we should be within the boundaries. We have not much ways to dissipate heat. Instead, using heat capacitors, so big blocks of mass through which we can store some thermal energy for a while, or play a bit with the duty cycle. So try to not overlap high power consumption components, or also to place them far enough one to each other. Or again, we can somehow try to play a bit with the radiation inside, but this is quite more complicated because, as you see, the satellite is quite packed, so we have no much new factors inside. Anyway, yeah, it's been an issue from the beginning, because if you go highly insulated everything, it's not going to work in orbit. If we leave a radiative path, let's say, to dissipate the heat, but that is bad because we have also incoming heat during re-entry, so it has been complicated, but that was the let's say, the compromise we found.
So two questions there on the right, and one on the back. Starting in the back.
Hi, thank you for your presentation. So on slide 6, you mentioned that you're using aerogel for your installation of the re-entry module. Have you done any work on the mechanical strength of the aerogel? Because, as you mentioned, it's very brittle. And
first of all, sorry, I cannot see you speaking. Okay, I'm sorry. We know, yeah, it's brittle and it's soft, so that's why we want to enclose it in the titanium box. The mechanical tests are not started yet. Basically, we didn't do any hardware test about that so far, besides the torque one. But yeah, it's in our mind to do it in the next phase. We are already procuring material and different kind of aerogel to see the best solution possible. But yes, we want to do, of course, mechanical tests. Anyway, all the aerogel part will be enclosed in something. So either is the titanium box, either is the ceramic box, but will not be free to spread dust around the satellite, that's for sure.
thank you.
Two in the front, and then one in the back. And
A lot of questions.
you planning to record and transmit temperatures of some critical parts inside the survival box during re-entry?
We do, yes. There are thermocouples both outside and inside the survival unit, close to the sidewalls, to the cork nose. So we are, don't remember the exact number, but we are literally a big number of thermocouples, and it's a matter of great interest to measure that.
Yeah. Okay. Here.
Just in the front on the right.
Hey. Hello.
Sorry, there is the light.
Yeah. Thank you for your presentation. I just interested in your, because right now you have two in your modeling you have I should say two conditions. One is the boundary condition that's simulated by CFD. Yeah. And I don't know what's the error or uncertainty of that result. And the second one is, because in your analysis results, we can see, for example, like the data acquisition system, and it will over the maximum temperature limits. But right now you said, okay, that the duration is acceptable. But if we take into account the modeling uncertainty, then maybe the duration could be shorter. So I don't know, in the future, do you have a plan to apply all the related tests to verify, to reduce all this uncertainty?
Well, about the CFD analysis, honestly, I cannot understand. I mean, I could, but I will not be reliable. It's something I didn't do, and it's not exactly my field. So I'm not sure about the uncertainties of that. What I'm sure about is that this is a worst case scenario. So we took the worst case to do the simulations. That's, I mean, it's the normal practice, but it's also common sense, because otherwise, as you said, we risk to go out of boundaries just because we neglect the margins we have. So we should go to the worst case. Nevertheless, as I said, the design has to be consolidated during the coming months. So of course we're going to refine this thermal analysis, but also we're going to refine the CFD analysis once we have found the definitive layout of the satellite in every detail. So yes, we want to refine the conditions, and yes, we're going to use again worst case scenario for every simulation.
There is also a question in the back. It will be for the coffee break.
Awesome.
So thank you
I will
again.
be pleased to answer anyway.
Thank you.